Welcome to Multiple Choice Monday number 19, and this week we are looking at free radicals. And so we got our correct answer as D. Let's have a look at why the other three are not true, and always note when a question says always true for free radicals that it could mean that it's sometimes true but not always. And that would be the case for A. So we should know that a radical is a species, and we'll come back to that word species in a moment, with an unpaired electron. And so in theory that could be in the s orbital if the element has electrons, well, just like s electrons in its outer shell. But it could and is much more likely to actually be in the p subshell. And so actually the reason for that is that s-block metals are very unlikely to form radicals. So it's much more likely that the unpaired electron is in p. The reason for that is because Group 1 and Group 2 metals, as we know, have low ionization energies, low first and second for the case of Group 2, which means they're pretty unlikely to just have this outer electron without losing it, or in fact delocalizing it as they do. So they're not counted as radicals. Okay. Made up of only single atoms. Well, let's go back to our definition. Our definition at the top, a lot of people talk about atoms with an unpaired electron when they define radicals, but really I use the word species. And the reason I use the word species is it can refer to more than one thing, atoms in this case, or molecules. So the atoms could be covalently bonded. Examples of that you should know, that when, for example, the chlorine radical comes along and reacts with an alkane, such as methane, in the first propagation step of our free radical substitution, you make a methyl radical and HCl molecule. So that is a molecular radical. Only one of the atoms has got the unpaired electron, but overall it's just a substance that overall has an unpaired electron. Okay, C is wrong because it's not heterolytic. It would be homolytic fission. So the way to think of this is hetero means opposites. And so with hetero meaning opposite or different, what you get with heterolytic is a positive ion and a negative ion. So for example, if you had HCl and you broke that bond, you would end up normally with an H plus and a Cl minus. That would be heterolytic fission. But we're talking about homolytic fission, for example, when a chlorine molecule, there's no polarity in that bond. When UV light breaks it, we get one electron going to each side, and so we make the same type of species. They are both radicals, so homolytic meaning same. And then they are uncharged. That is absolutely true. So you can't have an ion and a radical, and I think a lot of people sort of miss this off. In fact, one of the ways to spot if something is a radical is to see something that you think would normally be an ion. For example, if you see OH without a charge on it, that is a radical. And that's because hydrogen has one electron in its outer shell, oxygen has 6. So once oxygen forms one bond with hydrogen, it's got one unpaired electron left over. Whereas if we added an electron to that and made OH minus, that would now be an ion. So the thing about ions is that normally stable ions, the reason they're stable is because they do not have unpaired electrons. And so therefore radicals are going to be species that do not have charges, either just atoms like chlorine or fragments of molecules like CH3, where we would normally expect another hydrogen to be sharing an electron with the carbon. So if you are needing to brush up on your mechanisms, I've just got, I think, about one space In my first masterclass this Saturday, which is looking at the first year stuff, including free radical substitution, along with electrophilic addition, nucleophilic, I've got a few more spaces in the second class where we'll be looking at the more A-level content, carbonyls, benzene, synthesis, and those terrifying unknown mechanisms. Drop me a line as soon as possible if you want a space on those, because, as I said, there's not many left. Practice exam style questions, videos on my website, and of course keep following me on Instagram and Facebook for more revision help.